let's get started today. We are, I wish I could whistle better. Okay, so we are kind of making a transition today pivoting away from kind of the programming part of databases and pivoting now toward the design and implementation of databases. So for the first few weeks of this semester, we talked about how to program in SQL, and we talked about the theoretical foundations of the relational model. And then last week, you went through the relational algebra and the relational calculus. The relational calculus forms the basis for SQL. And way back when in the second week of the course, when we went through chapter 4 on the relational model, that covered the DDL, or the theoretical foundation for the data description language for databases. So we've now done that, and you should have an idea of how to write queries and how to manipulate a database. What we're going to, and that's kind of what the user of a database does. What we're going to be doing for the next 3 to 4 weeks is talking about how one designs a database, so how one actually decides what should be a relation, what should be the attributes in a relation, what should be the primary key, what should be the foreign key. So we're going to talk about those kinds of considerations. And then we'll talk also about physical design, which is how we actually implement a relation on the file system so that we can access information efficiently, how we can allow the query optimizer to efficiently satisfy queries. So the next 3 weeks is going to be pivoting toward design. It isn't really going to have much to do with programming at all. Before we do that, I just wanted to quickly say a couple things about the relational calculus, because I know it seems intimidating to many of you, just the name and the terminology. It's with all the math. And there's just a couple things in the video lecture I wanted to emphasize, because I think it helps when you're doing the homework with the relational calculus. So the first thing that I think it helps to think about, wait a minute, something's, okay. Okay, so one is, if you're having problems, think about how to express the query as an SQL query. And then convert to the relational algebra or calculus. Okay, and there's some basic things when you're doing the conversion. So if you have something like select, say, A comma B from, say, hotel, where, and I'll just do that, okay, or where predicate. Then there's just some basic stuff. The A and the B are going over here to the left of the bar. It's the attributes we're selecting. Anything in the from statement is a tuple variable. So you're just saying things like hotel is actually hotel is not the tuple variable, it's the relation, but in parentheses you put the tuple variable. And here you often use an alias. You'll say hotel as H. Well, you can just think of the as H as a tuple variable. Okay, so all the tuple variables are simply separated by ands, and then and the predicate. So the predicate kind of goes in parentheses. The where clause is an and that's appended to the tuple variables. So that's kind of a pretty basic mapping from a basic SQL query to a relational calculus query. So the attributes just go to the left of the bar. The relations, each of them is going to be a tuple variable, and then the predicate gets put into this and. Now, I'm not going to go into the whole, I'd have to go into 15 or 20 minutes of how to do joints. I'm not going to do that here. I'll refer you to the video lecture for how to do a join, because that involves some using for their exists and the like. But that's the basic conversion from an SQL query to a relational calculus query. So the second thing I want to make a big point about, because it seems like no matter how many times I say it, students get it wrong on the tests, so maybe you should write it down. Chapter 4, and in general, the relational model equals the theoretical basis for the DDL. And it is the relational calculus, not the relational algebra, that is the theoretical basis for the DML. Okay, which is SQL. Okay, it is not the relational algebra. So often on exams, students put down that the relational algebra is the theoretical basis for the DML. It's not. It's the relational calculus. The relational algebra is derived from the relational calculus. And I know it's easy to think that the relational algebra is the theoretical basis because when you write those relational algebra queries, they look so much like SQL. And when you write those relational calculus queries, somehow they don't seem like they're from SQL. But the relational calculus really is the theoretical basis for the DML, and it is what SQL is modeled on. It's not modeled on the relational algebra. Okay, so those are just three big points I want to make about the relational algebra, relational calculus, and the relational model. So, and I guess the final thing is there really are three different things. So this is the relational model. When I say that, I'm talking about the theoretical basis for the DDL. Relational calculus, which is the theoretical basis for the DML. And then the relational algebra is a procedurally oriented way of expressing queries. The relational calculus is a declarative way, meaning you don't say how to perform the operation with the relational calculus. But with the relational algebra, you do. You say this is a select, this is a project, this is a join. You don't do that with the relational calculus. The relational calculus is higher level. Okay? The relational calculus maybe is like Java, and the relational algebra is like C. C is much closer to the machine level. It's much more procedural. Java is higher level. Same thing with the relational calculus. The relational calculus is higher level. We say it's declarative because you don't specify how to complete the operations. The relational algebra does. The relational algebra is very specific about the order in which operations are performed and how they are performed. Okay, so questions about any of that? Okay. So in that case, let's move on to design. And It is what's going to concern us for the next couple of weeks. And the way that I tackle this is that, first of all, there's two different ways of doing design. One is to use top-down. So let's just quickly. So you have top-down design. And the technique commonly used for top-down design is something called ER modeling, which stands for entity relationship. Then there's a second technique that's called bottom-up design. And the technique normally used for that is normalization. You can go with whatever technique in the real world, you can go with whatever technique you're most comfortable with. If you're a top-down person, you'd start with ER modeling. If you're a bottom-up person, you'd go with normalization. I'm personally a top-down person. Most people seem to be. So most people seem to start with ER modeling and then use normalization as a check. If you start with normalization, you do the same thing. You typically use ER modeling then as a check. So one becomes your primary tool and this other becomes the secondary tool for checking your work. And each of these we spend a week on. The first day, like today, is where I go over all the concepts, and the second day is when I go over a case study. And what I found when I first started teaching the course, I just went over the concepts and I didn't do a case study. And the results were horrible. The homework assignments were a disaster. The exams were a disaster. So it's really important, actually, that on Thursday you come here and we work through that case study together, because otherwise your homework's going to be a mess and the midterm's going to be a mess. Okay, so you may think I can skip out on Thursday because the case study is just a big example. If you skip out on Thursday, you're probably bombing both the midterm and the homework assignment, just so you know. Okay. So, as I said, the ER modeling is, well, it's typically abbreviated as ER, but it stands for entity relationship modeling, because those are the two big things with it. Entities get translated into relations, and relationships are what define the foreign keys. So again, what we're doing here is we're talking about, you're given a problem description, and now you have to figure out from the problem description what should be the relations, what should be the attributes, and how should I divide the attributes among the relations. So I guess another thing I should say about design. So with design, what we're trying to do, what are we doing? One, we're enumerating the relations. Two, we're apportioning or assigning, I'll say assigning, attributes to relations. And the third thing we're doing is we are establishing or determining relationships among relations. So for example, a relationship might be branch has staff, or a branch employs staff. That's a relationship between branch and staff. Or staff manages properties. So there's relationships between these relations. So these are the three things we're trying to do with design, whether we're doing top-down or bottom-up design. This is what we're trying to come to eventually, is a set of relations. and the attributes in those relations. And then there will be relationships among them that are determined by foreign keys. Okay, so with what we're talking about today, we're talking about the first four. What are the basic concepts behind entity relationship modeling? And there's something called the Unified Modeling Language, or UML, which is typically used to express designs that are formulated using ER modeling. So typically the designs are expressed pictorially using this UML language. Then there's a couple common problems called connection traps that arise with ER modeling, so we want you to know how to identify them. And then on Thursdays, when we'll talk about how to build an ER model from a requirements specification. So that's when we go through the case study. So the concepts of the ER model map rather nicely to those three ideas of design that I just talked about. So you want to identify entities, okay? And entities are going to map to relations. Okay, attributes obviously will map to attributes, and you apportion them among relations. And then relationship types are the relationships that we establish between the various entities. Okay, so these three things map very directly to what I was just talking about in terms of what we're doing with design. Okay, so an entity is the first big thing. It's a group of objects with the same properties that we identify as having an independent existence. And an occurrence is simply a unique object of that type. Just like so if you're familiar with the class instance model, the entity type is a class and the entity occurrence is an instance. That's an analogy that you can think of. Okay, so there are two different types of entities. There's those that exist in the physical world, like staff, branches, customers, parts, products, suppliers, customers. Those are physical things existing in the real world. Then there are things that have more of a conceptual existence, things like a viewing of a property, an inspection of a property, a sale, a work experience. Those aren't quite physical things that I can put my hands on. Now I know that we translate some of these conceptual things into physical documents. The way that we finalize a sale is by signing a contract, and that typically occurs on a piece of paper, although these days it could be virtually done through an electronic document. Or a viewing, the customer might have written something on a piece of paper. So it is true that there may be a physical artifact that results from this conceptual existence, but it's not normally something that you can physically touch. We may create a physical artifact to record its existence, but its act is not typically something that's physical. The sale is something we negotiate. It's not physical. It's intangible. Okay, and it also turns out that many of these things that are conceptual end up being relationships as opposed to entities. So an important point is that many of these end up as many of these conceptual entities are really relationships. And I don't like the fact that the book actually calls them conceptual entities, but I'm trying to be consistent with the books. They are really relationships. And when we get to relationships, you'll understand this point better. So I'll defer the discussion of why. But many of these conceptual entities are really relationships among entities. Okay. Actually, as an example, a viewing is really a three-way relationship among a realtor, a client, and a property. Okay, the realtor takes the client to the property to view it. It's really a three-way relationship among a client, a realtor, and a property, or a sale. Okay, is really a relationship between a staff person and a customer and a product. A salesperson selling a product to a customer. So a sale is really a relationship among entities. So many of these conceptual entities are really relationships. They're not really entities. Whereas physical, things that have a physical existence, they really are entities and they become relations. Now, most of these conceptual entities also become relations. And so in that sense, it makes sense to speak of them as entities because typically each entity becomes a relation. Okay, so it's usually pretty easy to identify entities. Okay, and on Thursday, when we go through the case study, I'll show you how you go about doing that. Okay, but in general, each entity is going to be mapped to a relation. And in our UML, the Unified Modeling Language, the way that we represent an entity is with a rectangular box and the name of the entity in that box. So these are two entities here, staff and branch. So we call these ER diagrams. And the Unified Modeling Language, UML, is used to create these ER diagrams. Okay, so entities are represented as labeled rectangles. Next is relationship types. So they are meaningful associations among entity types, and then you can have a specific concrete occurrence. So we just talked about a sale. I could have a salesperson sell a product to a customer. Okay, that is, in effect, a relationship. And a relationship occurrence might be Brad Vanderzanden sells Jim Plank a computer. That would be a specific relationship occurrence where Brad Vanderzanden is the specific occurrence of the salesperson. Jim Plank is the specific occurrence of the customer, and a computer is the specific occurrence of a product. Okay, so each one being a participating entity type. In our ER diagrams, they are represented as a line between entities, and each relationship is labeled. And typically, the relationship has an arrow to indicate the direction of the relationship. And that arrow is normally in the direction of the entity that ends up having the foreign key. So when you create the entity relationship diagram, you may not know how to initially put this arrow here. Okay, and the book puts the arrow there. If you put it on the line, I'm fine. I don't care if you put it on the line rather than next to the label. Okay, but normally the direction is in the direction of the foreign key. So in this case, it is staff that holds the foreign key. Okay, each staff has a branch number. So typically, the relationship, we point it toward the entity that's going to have the foreign key. And another way to think of it is if one entity can have, if in the relationship there's only one occurrence of one entity, So here, there's only one occurrence of a branch, but many staff per branch. So if the other way is generally if there's in the relationship, if there's only one occurrence of one participating entity, and there are many occurrences of the other participating entity, then we typically direct the arrow toward the entity that is many. Okay? So again, you might think, well, wait a minute, there could be multiple branches. But what I'm talking about here, remember, we make a distinction between a relationship type and a relationship occurrence. What I'm talking about here is a relationship occurrence. So when you have a relationship occurrence, you have only one branch in the relationship occurrence, but you can have many staff members in that relationship occurrence. So you direct the arrow towards staff. Now, another thing about relationship names is you want them to typically be action verbs. So has isn't particularly good. Employs would probably be better. Okay? Because has is passive. In English, has is more of a passive verb. You try to select action verbs for your relationships. If you find yourself using a passive verb, it may well be that the arrow is in the wrong direction. So for example, if I drew the arrow from staff to branch, then I would be more likely to say staff belongs to or staff is employed by. Those aren't as active. Okay, I'm having to use multiple words to describe that relationship. Staff belongs to branch or staff is employed by. I'm using passive verbs. I'm using multiple words for the relationship. If I can't express the relationship with a single action verb, perhaps flip the two entities and see if it makes more sense to express it the other way. And that's the direction you draw the arrow. If I say branch employs staff, I draw the arrow from branch to staff. Okay, so again, this is just going to, next slide. Actually, it doesn't quite codify all that. So there can be more than two entities in a relationship. This showed what's called a binary relationship. But I gave you already two examples of ternary relationships. That sales relationship was a ternary relationship because it involved three entities: the salesperson, the customer, and a product. The viewing relation was a ternary relationship. It involved a realtor taking a customer to a property to view it. There were three entities: the realtor, the client, and the property. So those are ternary relationships. They involve three entities. A quaternary relationship involves four. A quintenary involves five, so on and so forth. It's pretty rare that you get beyond four. To represent a binary relationship, you've already seen it. Just a line between the two boxes and an arrow. Once you get above two, you use a diamond to represent the relationship. So if it's a binary, you just draw a line and you have a directed, it's basically a directed edge. But once you go above binary, you now use a diamond to represent the relationship. And what other thing do you notice that's absent here? No arrow. So it's no longer directed. Okay, so it's an undirected relationship. So if it's beyond binary, you use a diamond and you do not direct it. So this is an example of a staff member registering a client at a branch. So when you get a new customer, that's the registers. Okay, here's one from hotel, the booking is actually a three-way relationship. A guest books a room at a hotel. So actually, even though there's 4 relations in that hotel database, the booking relation is actually a relationship among the other 3. The guest, the hotel, and the room are all entities, and the booking is really a relationship among those 3. This is the wrong way to show a ternary relationship. You might be tempted because you know that booking is a relation to also draw booking as a rectangle, but that would be wrong because booking is a relationship. So you do this on an exam or a homework assignment, you'll get points deducted. You do it in the real world and your boss is going to tell you it's wrong. Okay, this is not the right way to write it. Even though booking gets eventually translated into a relation, that's not how it's shown in the ER diagram. It is shown that way, as a three-way relationship using a diamond. Okay. And here's an example of a quaternary relationship. So we have remember, the authors are Irish, I believe, and so solicitor is kind of an English term. Solicitor arranges a buyer to make a bid, and that is supported by a financial institution. So if you bid maybe for a company, you line up financial support, and you might have an advisor helping you with it. So that's a 4-way relationship. Maybe J.P. Morgan is the financial institution. Maybe Goldman Sachs is the solicitor. I'm the buyer making a bid for some company. In fact, the company probably would, although the book said bid, probably what it really would be is bid would probably be here, and company would really be what's down there. In fact, I can't change it because it's the slide that the company did. At any rate, what I would prefer is that this really be company and that be a bid. Because that's what it... No, you're already here. You don't have to head northwest anywhere. Okay. So probably I would prefer it be written like that. Solicitor arranges for a buyer to bid on a company, and that's backed by some financial institution. I guess the bottom line here is there's subjectiveness in here. The book's authors would have written this UML diagram differently than I would. Okay, so there's not always a right answer, although of course you'll be graded that way on the homework in the exam because I have an idea of what the right answer really does look like. But in the real world, things aren't always cut and dried. Okay, we can also have recursive relationships where the same entity is on both sides of the relation. So here's an example. A staff member may have a manager. So we may have the relationship of a staff member supervising a staff member. So that is called a recursive relationship because both sides of the relationship have the same entity. And in the relation for staff, you might have in staff, it might have manager. Might be one of the attributes, and the manager is actually simply a staff number. Okay? So that's how that's the foreign key is, in that case, a staff number. So when we have this recursive relationship. Not only do we put a kind of loop in there, but we may also label the relationship with the roles to make it clear what the two roles are. So here we're saying that supervisor supervises supervisee, and it goes from supervisor to supervisee. So in the UML diagram, a recursive relationship, you often, in addition to having the relationship name, you often also put the roles down so it's clear what the two ends of it mean. Otherwise, you're looking at staff goes to staff, what the heck? May not be clear what's going on. Okay. Although, quite frankly, if you said supervises or manages and left off supervisor and supervisee, I think most people would understand what that means. So I wouldn't, if, again, this is subjective, but if you think that the verb you've used is very explanatory, there's really no reason to put down the roles. But if the verb can't really completely convey the sense of what that relationship is, that recursive relationship, then you should label the roles. Okay, and sometimes the relationships there's two different relationships going in different directions. So here's one where the branch has staff, but also staff manages branch. Don't make it a double-ended edge. Instead, it's two separate edges, and each edge is appropriately labeled. So staff manages branch, that goes to the right, and that's a one-to-one relationship. There's only one staff managing one branch. So in this case, you're going to have to use the foreign key to figure out the direction of the arrow. In this case, the branch is going to have the foreign key. It's going to have a staff number in it indicating which staff member manages it. Okay? So if you can have relationships going in both directions between relations, make sure that you separate them into two different edges. Okay, and again, you might or might not decide to indicate what the roles are in that case, to disambiguate if there's any ambiguity. Okay, so that's relationships. We'll come back to them in a moment. Okay, attributes we've pretty much already covered. So an attribute is a property of an entity or a relationship type. Okay, and we will show you, so as an example, a booking. Not only does it express a room, a hotel, and a guest, but it also has booking dates. A date from and a date to. So date from and date to would be considered attributes of the booking relationship. So relationships are also allowed to have attributes. And this is a little bit new. We can have either simple attributes or composite attributes. So simple attributes are a single component. Composite attributes can have multiple components, each with an independent existence. The classic example of a composite attribute is an address. So you might have an entire address as 1678 Cardiff Road, Columbus, Ohio, 43221. That's a composite address that has a street address, has a city, has a state, and has a zip code. Has 4 attributes, each with a physical existence. A zip code has its own, independent existence. The city has an independent existence, a state has an independent existence, and a street has an independent existence. You might even argue that the street address by itself is a composite attribute, because you might consider the number and the street name to be two separate things. I might want all people on Cardiff Road. So you might actually consider the street address itself to be a composite attribute. The reason I mentioned that is so that you can see that a composite attribute might actually itself be composed from composite attributes. Okay, and then orthogonal. So we often talk in computer science about orthogonal things. You can also have single-valued attributes and multi-valued attributes. So a single-valued attribute has a single value for each occurrence of the entity type, and a multi-valued attribute has multiple values for each occurrence of an entity type. So a phone number is a classic example of a multi-valued attribute. A branch might have multiple phone numbers. Now, a phone number could be considered a composite attribute, right? Because a phone number consists of an area code and a local number. Even that 3-digit number has there's 3 groups. The area code, I forget what the 3-digit number is called, and the 4-digit number, but even the 3-digit number has some meaning. But at the very least, you can talk about an area code and a local code. Okay? And then you can even talk about a country code. The US is 1. So that's why I called them orthogonal. So you could have a multi-valued attribute, and that attribute could be a composite attribute. Now, multi-valued attributes cause problems for us. Why do multi-valued attributes cause problems for us? Very good. Because you can't store multiple values in one cell of a table. So you have to find a different way to handle that. And as it turns out, what we typically do is we move the multi-valued attribute into its own relation. So for example, if we have phone number, we would probably have since it's multi-valued, we would probably create a separate relation called, for example, directory. And directory would have 2, one's branch number and telephone number. And now you could have a branch B003, each with, now each cell has only one value, but you're able to get, now each row represents one value of the attribute. Efficient? No. But that's the limitation imposed on us by the relational model. Another classic example of that is dependence. If a person has dependence, again, that's a multi-valued attribute. Some people have no dependence, some people have many dependents. So again, you might have staff number, maybe name of the dependent. So that'd be another. Dependence would be another example of a multi-valued attribute. And the typical solution is to represent the multi-valued attribute as a separate table. Okay, you can try to figure out what is the maximum number of that attribute, and then you could have one field for each possible one. So you could have branch, and if I determine that there can be at most 3 phone numbers, you might have telephone number 1, telephone number 2, and telephone number 3. That's just a horrible solution, though. Creates all kinds of problems. First of all, there's often a lot of nulls in there. which means you have wasted space. Secondly, it complicates your queries because now you're having to say equal telephone number 1 equals or telephone number 2 equals or telephone number 3 equals. And guess what? Some people have a lot of dependents, so you might have to come up with like 15 fields. And now, if you want to check whether someone has a dependent named Brad, you're going to have to say where name 1 equals Brad, or name 2 equals Brad, or name 3. You get the point. It's pretty bad. And of course, then you get the rare case of someone who has more than 15 dependents, and now what do? You're out of luck. So trying to cram a multi-valued attribute into a relation by simply figuring out the maximum number doesn't work well for a whole slew of reasons. Just put your multi-valued attributes into separate relations and it works perfectly. The foreign key is going to link back into the main relation. Okay. And okay, so we've had two types of attributes so far. We have whether they're simple or composite, single valued or multi-valued, and the third characteristic, are they derived or not derived? So derived means that it's derivable from the value of a related attribute or set of attributes. And they don't even have to be in the same entity type. So let me quickly go to, whoops, I don't have examples. So let me give you examples. There we go. So here are 3 examples. I know it may be a little hard to read, so I'll talk about them. So the first type of derived attribute is an aggregate attribute. It could be total staff count. Okay, so I'll write in bigger words. Aggregate attribute. So the result of an aggregate function. Okay, it could be the average salary, the average number of property. That's not right. We'll get, so result of an aggregate function. The next might be an attribute computable from 2 columns in the same relation. So an attribute computable from 2 columns in the same relation. So a good example of that, in the booking relation, we often care about the number of days that a guest stayed with us. So we could easily have a derived attribute called number or length of stay. That's a derived attribute because what can it be derived from? Date from and date to. If you subtract date from date to, that gives you the length of stay. So we typically aren't going to store this derived attribute because it can be derived from other attributes. That's why we call it, though, a derived attribute. Okay? The third type of derived attribute is an attribute, I'm going to use quotes here, computable from 2 columns, or I'll say from columns, in different relationships, in different entities, or in different relations. So you had to do this actually in one of your homework assignments where we may care about the revenue derived from a guest. Well, in order to calculate the revenue derived from a guest on their stay, we need to know about the length of stay, which we can get from the booking relation, and we need to know the price of the room, which we get from the room relation. So that's a derived attribute where we multiply the price from the room relation with the length of stay from the booking relation. Or if you don't, you could even say it's a 3-column relation. It's room price times booking to minus booking from, or date from minus date to minus date from. The point is, it's an attribute derived from columns in different relations. So those are the 3 major types of derived attributes. One's from aggregate, derived from aggregate functions. One's computable from 2 or more columns in the same relation. One's computable from columns in different relations. We normally do not store derived attributes explicitly, and the reason is because they can be derived. And in fact, because they can be derived, what would be the problem with storing a derived attribute in our relation? You have to make sure you update it, otherwise you get consistency issues. So you typically don't want to store it physically in a base relation because it's likely to get you inconsistency. Now, these derived attributes often show up in views because you often care about them in views. But views get maintained by the system whenever the underlying base relation changes. So that's something the database takes care of for you. Okay, now showing all of this in an entity relationship diagram, you can see that a composite attribute you kind of indent. So you list the name of the composite attribute and then you list its subcomponents by indenting them. A multi-valued attribute, you list it and then in brackets you put the minimum and maximum number of values for that attribute. For dependence, it might actually be 0 ... star, meaning it can be 0 to as many as possible. A star indicates we don't have an upper limit on the maximum number. And the slash before the attribute right here, this total staff, has a slash before it that indicates a derived attribute. And again, a derived attribute is typically not physically stored. Now, you don't typically put the names of attributes in a ER diagram because it becomes too cluttered. But if you do, this is the way you do it. I don't want you to put attributes into your ER diagrams on the homework or on a midterm, okay, because it clutters things up. And also, you tend to put, if you do show the primary key, you call it PK, and you put it in braces. So the multi-valued attributes go in square braces. The primary key goes in curly braces. So that's the other thing you have to do with your attributes is you identify your candidate keys. Remember, a candidate key is the minimal set of attributes that uniquely identifies each row or each occurrence of an entity type. The primary key is the candidate key that you choose to uniquely identify each occurrence. And this is a new concept. A composite key is a candidate key that consists of 2 or more attributes. Again, we typically like our primary keys to be single attributes because they take up less storage, and we often will create artificial keys so that we can avoid having composite keys. In the booking relationship, remember we typically had to have 3 attributes to uniquely identify a booking. It would be like guest number, actually it'd be 4. In a booking, you need guest number, room number, hotel number, and a booking and a date from or a date to. So that was 4 attributes. Big composite key. So that's why you often invent artificial keys, so you don't have to go with enormous composite keys. Okay. Okay, so that's a lot of the ER. So you've been introduced now to the 3 basic types of ER things in the entity relationship model: entities, relationships, attributes. And I've shown you how you represent them in an ER diagram. So entities are labeled rectangles. Relationships are edges, either directed or undirected. If you have a relationship that's more than a binary relationship, you represent it using a what? Diamond. And attributes typically are not shown in the ER diagram, but if they are, they're shown as you see them there. Okay, now going to dive a little more deeply into each of these 3 components: entities, relationships, and attributes. So the book makes a distinction between a strong entity type and a weak entity type. I find this to be somewhat nebulous, but they call a strong entity type an entity type that is not existent dependent on some other entity type. And a weak entity type is existence dependent on some other entity type. So those conceptual entities that I showed you at the beginning, like sales, inspection, viewing, those would all be considered weak entity types because they depend on the other entity types for their existence. In the hotel database, you could make which of the 4, well, booking is certainly a weak entity type. You might make the claim that rooms are a weak entity type because they depend on the existence of a hotel. You close the hotel, all those rooms go away in that hotel. So you might make the claim that the rooms entity is actually a weak entity type because its existence depends on the hotel entity type. This is one thing that I will not test you on because I think it is so nebulous. But you should be aware of it because people will talk about strong and weak entity types. Okay, I think it's very subjective as to what is a weak entity type and what is a strong entity type. I'm just trying to give you examples so that if you use these terms in the real world, someone doesn't look at you like, what the heck are you talking about? Okay, in the book, they give as an example of a weak entity type preference. So the client might express preferences for a certain type of unit, like a condo or townhouse or detached dwelling or apartment. They might put a preference on the maximum rent. They might have a preference for number of bathrooms, number of bedrooms. They might want a swimming pool. So they might have a set of preferences. We call the preferences a weak entity because without the client, the preference would not exist. Now, in practice, if you show a weak entity like this, the weak entity typically does not have a primary key. And why is that? Because when you map it to a relation, the weak entity will get a foreign key, and the foreign key will point back, in this case, to the client. So when this entity, this preference entity, is realized as a relation, it will have a third attribute called client number, and that will be a foreign key pointing back to the strong entity. Okay, now, so that's the one thing delving into entities. Now delving into relationships. They are the ones that tend to give you the most problem. When you're trying to determine what are the relationships in or from a requirements document, you need to extract the relationships. This is the thing that will give you the most problem on an exam or the homework. So first of all, just some stuff. If a relationship has attributes, you list the attributes in a separate box with, as you can see here, you don't actually label the top because it's not an entity. So it looks like an entity, but it's not. You list the attributes, and then you attach it to the relationship line with a dotted line. So in this case, we say that a newspaper advertises property for rent, and it has the date of the advertisement and its cost as attributes. If I had the booking relationship, that would be I would have date to and date from, and you would see a dotted line coming into the diamond in that case, because in that case, booking is a diamond. Okay, then we talk about constraints on our relationships. So remember that when we were talking about the relational model, we said that you can have constraints. And one of the types of constraints are business constraints. Like a staff member can manage no more than 100 properties. Or at most, one staff member manages a branch. Or a staff member can manage at most one branch. So in the ER diagrams, we talk about those so-called business constraints as structural constraints. And the main type of constraint we talk about is multiplicity, which is the range of possible occurrences of an entity type. So for example, a staff member can manage anywhere from 0 to 100 properties. So we call that the multiplicity, and as I said, that represents the policies or business rules established by the company. And multiplicities are made up of two things because they have a minimum and a maximum value. The maximum value is the cardinality. The minimum value is the participation. So this is the max. This is the min. And you will see, so we call cardinality max, we call participation rate min, so those were just the terms assigned. You got to get used to the jargon. So here, the bottom 0 to 1, right here 0 to 1, 0 is the participation rate, 1 is the cardinality. And in our diagrams, we typically label our relationships with the multiplicity. So in this relationship, a staff member may manage a minimum of 0. Most staff members manage no branches. But if they do manage a branch, they may manage at most one branch. So we write it as 0 dot dot 1. The dot dot being the, why they don't just say 0 to 1, dash 1, I don't know, but it's dot dot. Then the other way, so it's in both directions. So with the staff, a staff member may have a minimum of one person managing a branch. So a branch must have a manager, and a branch can have at most one manager. So it's 1 dot dot 1 to indicate that there's a minimum of one manager and a maximum of one manager. So this is the number of entities that may occur in one instance of that relationship. Okay? And when I first started with this I really struggled with. So you may struggle with it too. And I struggled with where to put these numbers, whether they went, like I wouldn't know whether 0 to 1 went next to branch or whether it went next to staff. Okay? So it is my way of finally resolving it was I would always put it in a sentence. I would say that if I wanted to figure out what this number right here was with branch, I would try to figure out what is the minimum and maximum number of branches that a staff could manage. So I'd say a staff manages, what is the minimum number of branches? Well, they might manage 0. And what is the maximum number? They might manage 1. And to get this number, the same thing. Now I think of branch as being the primary. So a branch is managed by, and in this case, it must be managed by at least one individual and by at most one individual. So what I would do for me to figure out these cardinalities is I would actually put the dependent thing second in the sentence. So this is the dependent now. And this is what I'm trying to figure out the multiplicity for. So I would actually make it the dependent thing in order to figure out how many occurrences of it could happen. And that's what worked for me. Whether it works for you or not, you'll just have to figure it out. But it really did. For a couple years, I really had trouble figuring out whether the number went here or the number went there. And I would keep flipping them around. Yes, Luke?
Is that assuming there's another edge the other way, too, though?
Not here, we're just showing that one particular relationship. You're right, there is a second relationship of branch employs staff, but that's not the one we're showing here. Okay, we'll get to that. Right here, we're just worried about that one relationship. Is that answering your question or not?
All of it. I guess kind of.
There's two, remember, there's two relationships between staff and branch.
Yeah.
There's one where the branch employs staff. That's not the one we're showing here. The one we're showing here is the managerial one, where staff manages branch. And we're just showing this one right here so that you can just focus on this one relationship. Okay? Other questions about this? Okay. So there are, no, let's go back. So if, let's say we did have a employs, okay, now a branch presumably employs one to many. So if it is unbounded, again, we use a star, so we say it employs one to many. And a staff, we might say, belongs to exactly one branch. So when it's one count dot dot one, it means a staff belongs to exactly one branch. A branch can employ one to many staff. Okay, I think I have an example. I'm going to flip forward a few slides. Okay, there, we've already covered that. Okay, here's another example of one that has multiplicity. So a staff can oversee 0 to many properties. A property may be overseen by 0 to 1 staff. So maybe when this property is first coming in, it hasn't yet been assigned to a realtor. So at that point, maybe it's 0. Okay. Again, you have to really, when you're doing these diagrams, in the real world, you have to make sure that you interview the right people and that you get this information. You don't just assume that a property must be overseen by someone. You ask and make sure, is it always going to be overseen by someone, or could it temporarily be null? So you need to ask. You don't make assumptions. Here's an example of what's called a many-to-many relationship. So a newspaper may advertise one or more properties, and a property may be advertised in 0 or more newspapers. So in this case, you can have multiple occurrences on both sides of the relationship. So you may say, well, under what circumstances would a property for rent be advertised in no newspaper? There's a good answer for that. Pardon? When it's already rented. Okay, why advertise when it's leased? So it won't be advertised when it's leased. But then when we're trying to lease it, we'll probably advertise it in multiple newspapers. Now with a newspaper, we typically, if we're not advertising a property for rent, why is it in our database? So typically we're advertising at least one property. Okay. Now, the book does something else that's confusing. And that is, it also refers to the degree for relationships, which is a different term than multiplicity. Again, orthogonality. Multiplicity is the number of occurrences of an entity in a relationship. When we talk about the degree of a relationship, so when we talk about the degree of a relationship, what we're talking about is the maximum or the cardinality of each of the two entities. So there are three types of relationships: one-to-one, one-to-many, and many-to-many. Okay, so, whoops. And again, that refers to the maximum cardinality of each one. So we say that the manages relationship is one-to-one because the maximum cardinality of each is 1. That's a one-to-one relationship. This property relationship is a one-to-many because one staff member is the maximum on the staff side, but star is the maximum on the property side. So this is a one-to-many relationship. And the newspaper advertises is a many-to-many relationship because in each case, the maximum number of entities is unbounded. So we say it's a many-to-many relationship. Okay? And this is the wrong way to show a many-to-many relationship because I know I just need a couple more minutes, then I'll let you go. But you don't show a many-to-many relationship by putting a entity here, even though it will probably end up as a relation. Some of you also will want to represent a many-to-many relationship as a diamond. That's also wrong. If it's a binary relationship, it is a line. You only use the diamond operator for when 3 or more entities are involved. But some of you get confused and think that you use a diamond for a many-to-many relationship. You don't. Okay. One last thing. I know that I'm over. I'm sorry, but I do need to get through this. So if you have a 3-way or more relationship, something like this, what you do in order to get those numbers is you hold the other two entities constant. I like to think of it like a function. So if I am trying to find the multiplicity for C, I say that I have a specific value for A and a specific value for B, and then I just try to determine what is the minimum number and the maximum number of occurrences for C if I have a specific value for A and a specific value for B. So here, a staff registers a branch, a client with a branch. Let's say that Brad registers Smiley with the Huntington branch. Well, or that Brad registers Smiley. How many branches can Brad register Smiley with? It's exactly 1. So it's a minimum 1 and a maximum of 1. Okay? Brad's at the Huntington branch. How many clients can Brad register at the Huntington branch? 0 to many. If I'm a bad staff member, I register 0. If I'm a good one, I register many. Okay? What about staff? Well, if I have a client, Smiley, who's registered at the Huntington branch, exactly 1 staff member registered Smiley at the Huntington branch. So again, with a multi-way relationship, you fix the values for all but one of the entities, and then you determine the minimum and maximum values for the remaining entity. Now, I know we didn't get to traps. There will be at least 1 or 2 questions on the quiz today, so make sure you do go through the slides. I don't think the slides are difficult, and I will go through the slides on Thursday. I'm only asking you for definitions on the quiz. So that shouldn't be hard to get on the quiz because it's just definitions.